So the plan today is that for the first half of the lecture, I will tell you about D-branes in Calabi-Yau manifold. So in the last lecture, we discussed D-brane in flat spacetime. So it's useful to know how to think about that object in a more general setup. And then I will change the subject, and I will start introducing the notion of AD-SCFT correspondence, which is a concrete top-down construction of the example of holography in quantum gravity in the context of string theory. So let me, for the first half, I will tell you about D-branes in Calabi-Yau manifold. Okay, so we consider some Calabi-Yau space, and in general, it's complex n dimension. And we consider some string theory, string propagating in this Calabi-Yau space. Okay. So the Walsh's theory in the NSR formalism can be described by n equal 2,2 superconformal sigma model. Okay. Symmetry is enhanced to 2,2, so that means that you have left n equal 2 supersymmetry, and you have n equal 2 right supersymmetry in addition to the conformal invariance. So the reason you have this enhancement is that, for example, for the left mover, you have two types of supercharges. One is given by this. And the other is given by this. And supersymmetry generator can be decomposed into two parts because you have complex structure. So you can distinguish the holomorphic coordinate with holomorphic index I and anti-holomorphic coordinate, where I and j goes from 1 to n. So for example, Calabi-Yau threefold, which we used in the context of heterotic string construction, a compactification to compactify 10 dimensions down to 4 dimensions. We had Calabi-Yau threefold, so n was 3. So and then Gij bar is a Calabi. Okay, and it satisfies the Calabi-Yau condition, which is needed for the conformal invariance. So we can make this distinction. So that means that we can assign different charges for these two supercharges. So these are, in the language of supersymmetry, these are called R symmetry. So in this case, R symmetry is generated by this U1 current. So with respect to this R current, psi has charge 1, psi bar has charge -1. So, so therefore, these have plus and minus charges, and those are explicitly shown with a sign plus and minus here. Okay, so these are interacting quantum field theories. So, for example, Gij bar is in general a function of x, the bosonic coordinate. So these are non-trivial quantum field theory in 2 dimensions, but this there is a universal symmetry generated by these currents. It is sometimes useful to bosonize this U1 current. So the notion of bosonization was discussed earlier when we discussed space-time supersymmetry of type 2 string theory. And the bosonization is an important part of the construction of supersymmetry. So this J is J satisfies a 2-point function relations like this. where n is this complex dimension of the Calabi-Yau manifold. And so because of that, it's useful to write it as square root of n I del of phi L. Okay, so that the 2-point function phi has this standard normalization that the phi L z, phi L w goes like minus or log of z minus w. Okay? So in addition, so if you remember the Hodge diamond of Calabi-Yau manifold, we have this Hodge diamond H11, H21, sorry, H00, H10, and Hn0, and then Hn1 all the way to H0n, Hn. So we have this kind of Hodge diamond. And for Calabi-Yau manifold, we have this, of course, if the Calabi-Yau manifold is connected, this is equal to 1. So therefore, this should also be equal to 1. This corresponds to the holomorphic n form. And one of the characterizations of Calabi-Yau manifold is that there is actually nowhere vanishing holomorphic n form. So these are n tensor. You have n holomorphic indices, and n is the maximum number you can have if you require this to be totally antisymmetric. And then it has this condition that del bar of omega is equal to 0. So I showed you when we discussed the Calabi-Yau manifold that if you have Calabi-Yau metric, the Rich-Pratt-Kähler metric, it implies the existence of the nowhere vanishing holomorphic n form. But conversely, it was shown by Yau that if you have nowhere vanishing holomorphic n form for Kähler manifold, then you can actually construct a Rich-Pratt-Kähler metric. Okay, so this is the essential ingredient. And one of the consequence of existence of this holomorphic n form is that you can actually construct additional holomorphic object. Okay. So you contract all the antisymmetric indices with size, and since these are fermions, so this transforms appropriately, and you can construct another quantity. So okay, so this is, I call that as omega, and omega satisfies the worldsheet holomorphicity equation. So this is another generator. Okay, and but each is, because of the Bosonization rule, you can actually show that this omega is equal to e to the I of square root of n of phi f. Okay, and you can check that this gives you consistent relation. That the relation consistent with algebra. And this phi plays a role. So phi L is important for space-time supersymmetry. Misspelled. Space-time supersymmetry. So the reason is that the space-time supersymmetry, of course, maps NS sector to Ramon sector, and vice versa. And one of the important ingredients, so you should do this. So in this case, for example, we are considering the situation where 10-dimensional space is compact phi to Calabi-Yau n-fold tensor with 9 minus 2n dimensional space. And you can, so we discussed how to construct space-time supersymmetry in 10 flat dimensions. So we have discussed this in earlier lecture. What we did was that to each direction we bosonized fermion. And then we consider exponential of bosonized operator. So we do that in this case also. So namely that you need a map. You need to construct an operator which maps NS sector for this sigma model to Ramon sector for this sigma model, and map that into each other. So that means that you have to bosonize fermion in this direction and construct space-time supersymmetry operator, but you also need an ingredient of this part. And for the Calabi-Yau N part, the ingredient you need is e to the plus or minus I of square root of n over 2 of phi. Okay, so this operator maps NS sector of the n equal to sigma model to the counterpart in Ramon sector and vice versa. So you combine this operator with the corresponding operator which maps Ramon sector to NS sector, vice versa, for this part of the sigma model to construct space-time supersymmetry generally. So this n equal to structure is essential in constructing space-time supersymmetry. And of course, we have the same structure for the right mover. So you have G plus GR plus minus JR and omega R. So I could have written this as omega L. Okay, and so this is a sort of a structure of n equal to sigma. Now, so how do you consider Calabi-Yau manifold with D-branes? So you may be interested in considering some structure, some object inside the Calabi-Yau manifold, and this can also be in general tensor with R 1,9 over 2n. So there might also be some structure in here. You can have some space in here, and you can have some space in here. The total space is the tensor product of this. D-brane might be extended over the tensor product of these spaces. But let's focus on this subspace. Okay, and then I will tell you what kind of subspaces we can consider. And then you ask, well, what kind of subspace, on what kind of subspace we can end open string. Okay, so we'll discuss the condition for this. Okay, so in order to understand what kind of D-branes we can have, we need to classify the boundary condition on the string worksheet. So the boundary condition on the 2 sigma model. Okay, so here I'm interested in the kind of boundary condition which preserves fraction of supersymmetry. So remember that there is actually a nice, so I forgot to say, there is actually a nice parallel between what happens in space-time analysis regarding supersymmetry and what happens to the worksheet. So if you remember the first analysis of Calabi-Yau manifold, what we saw was that suppose you have some general curved space. You asked what kind of space preserves fraction of supersymmetry. So the condition for the preservation of supersymmetry was or is existence of covariantly constant spinor. And we showed that the existence of covariantly constant spinor, which is required by supersymmetry, namely that we know that the transformation property of gravitino transforms under supersymmetry as derivative of supersymmetry transformation, local supersymmetry transformation parameter. And existence of supersymmetry requires integrability of this equation. And so that led to Calabi-Yau condition. So that was how Calabi-Yau manifold came from the perspective of supersymmetry. From the worldsheet perspective, the space-time supersymmetry requires basically existence of this free boson phi L, which is an essential ingredient, to construct an operator map from NS to R and vice versa. And that is guaranteed by n equal 2 supersymmetry. So n equal 2 supersymmetry guarantees that you have this operator which maps NS to Ramon in such a way that is compatible with this worldsheet supersymmetry. Okay? So this sort of mirrors between these two. And in fact, you can relate this operator to the covariantly constant spin. Okay? So that means that in order to preserve of a fraction of SUSY, so this is a space-time SUSY, requires that the preservation of e to the plus minus I square root of n over 2 phi left and right. So that means that inevitably the boundary condition has to be such that it identifies the phi left to be either plus or minus phi right. So that would correspond to the choice that the boundary condition therefore has to be such that you have either j left is equal to minus j right, or j left is equal to plus j right. So this has to be the boundary condition. So you have a binary choice of boundary condition, and this is required by consistency with the requirement that you preserve fraction of space-time supersymmetry. Either j left is equal to minus j right, or j left is equal to j right. And in fact, these are called A-type and B-type. Okay, and so this A and B are inspired by the terminology of type 2A and type 2B in a little bit subtle way. But so anyway, it goes like that. Okay, and so this implies if you induction requires that n equal 1 supersymmetry is half of the n equal 1 supersymmetry is preserved in order for the local worldsheet supersymmetry to be compatible. It can be either identification should be, so this would correspond to G plus on the right mover, G plus on the left mover is identified with the G minus on the right mover, and vice versa. And this would require G left plus to be identified with G right plus. Okay, so that this identification is compatible with this identification. Okay, so these are two types of boundary condition, and so that means that if you want to interested in putting D-brane on Calabi-Yau manifold in such a way that half of supersymmetry is preserved, then you need to consider boundary condition which satisfies these conditions. Okay, so then you can ask, well, what kind of geometrically what does it mean? So what it means that we are doing. So this is something actually when a notion of D-brane appeared this is something that I and my postdoc here on Oz and my graduate students, Jen In, were interested in. And so we went out to classify, try to understand what these conditions means. And so here is what we understood. So sigma model on Calabi-Yau manifold is in general interacting theory, so it's hard to understand it. But when the size of Calabi-Yau is very large and smooth compared to the string scale, then we can use perturbation theory. So we can start from there, and then we can try to go back and discuss more general Calabi-Yau manifold. But when the Calabi-Yau is smooth and large, so that the curvature length is much larger than string scale, then we can use perturbation theory. And the leading order is a free theory. So you can first ask, well, what kind of free theory satisfies this? So the idea is first, you ignore the fact that the G depends on X and pretend that you have just a Gaussian theory. And then classify this, and then you can start incorporating interaction. So we can try to do that. Okay. So let's try to first look at that question. Okay. So let's first try ask the following simple question. So suppose you first consider n equal 1 supersymmetry. So you just consider diagonal part of the supercharge. So that is equal to G mu nu psi left mu del of x mu. Yeah. So you have this where mu nu now goes from 1 to 2m. So these are real coordinates. Okay, and then you can ask, well, what kind of, and then you assume that G mu nu is constant. And you can ask, well, what kind of boundary condition preserves this half of the supercurrent? Well, suppose we choose the boundary condition to identify x mu to x bar nu. But suppose you want to be general, so you allow some linear combination of them, like that. And then you also try to sort of identify left and right. And in general, you can, of course, mix them with, even if you are interested in doing that in sort of linear superposition. In general, you can have a general matrix, but we'll see immediately that it's useful to use the same matrix to solve this condition that G left is equal to plus minus G right. Because you see that if you correct this plus minus with this plus minus, then this condition is equivalent to the condition that the G mu nu R mu rho R nu sigma is equal to 0 sigma. Okay. So from this, you see that you have this. So that means that the matrix R mu nu satisfies G mu nu R mu rho R mu sigma is equal to 0 sigma. So from this we can, and the R mu nu is a real matrix. So if R mu nu were symmetric, then its eigenvalue should be either plus or minus. You can diagonalize them, and its eigenvalue should be either plus or minus 1. But in general, and then, so if R is symmetric, the eigenvalues are either +1 or -1, and +1 corresponds to Neumann condition, and -1 corresponds to Dirichlet. And if R is not symmetric, then you can show that it gives rise to mixed Neumann and Dirichlet, and that is actually equivalent to turning on gauge field. On D-brane. Okay, so this is actually essentially the same as what we discussed in the last lecture. So the preservation of supersymmetry requires the boundary condition to be either Neumann or Dirichlet, or their combinations. Okay, so this will be the case when we can treat this space to be like almost like a flat space, and then this will be the situation. Okay, so now what if we consider more general situations? What if we consider more general situations? So suppose you have a Calabi-Yau manifold. And suppose you have some subspace gamma, which may or may not be straight. So in general, it's a curved space, so we don't have a notion of straight line or straight subspace, but there is some subspace. And then suppose we are considering a situation that the string can end on. Okay. So what kind of condition we can consider? Well, so it's useful to focus on this particular region and open it up. And then suppose, so this is gamma. So suppose I choose coordinate so that in this direction we have coordinate xa, and then in this direction we have coordinate y small a, where a goes from 1 to p, where p is a dimension of gamma. Okay, and then a goes from 1 to 2n minus d, where n is a dimension of Calabi-Yau, d n minus 2n minus p, so that the combination of xa and ya gives you local coordinate of the Calabi-Yau manifold. Okay, and then you can ask, well, what kind of condition? So suppose I choose this coordinate, and then ask, well, what kind of condition give rise to this? So so if you have A-type condition, then what this kind? So you can consider. Okay, so it's useful to actually introduce this scalar potential. A scalar form. It's useful to write equation in scalar form. So scalar form is defined to be Gij bar dxi with dxj bar. But it's useful to write this in the real term. So suppose I write it in the real term like this. So these are real coordinates, and we have this k mu nu. Then what we can see from these conditions is that if you have A type condition, then we have K mu nu psi left mu psi left nu is equal to minus of K mu nu psi left psi right mu psi right mu. Whereas if you have B type condition, we have K mu nu psi left mu psi left nu is equal to plus of this. So you can substitute this condition to this equation and see what this implies. So let's first look at the B type condition. So if you have B type condition, then if you have Kähler form, if you have a Kähler form like that, and in the case of B type boundary condition, so this is a Kähler form. If you have B type boundary condition, you have to have J left is equal to J right, and since J is given by contracting fermions with the Kähler form, so we get the condition that J mu, K mu nu, R mu rho, R mu sigma is equal to K rho sigma. And we also have this condition that omega left is equal to plus or minus. Omega left is equal to some phase times omega right. And this gives rise to the condition that omega mu1 to mu n, R mu1 to R mu n is equal to up to some phase omega of mu1 to mu n. So let's first look at this condition. So what does this condition mean? Well, so if I express this condition in terms of this coordinate, so if you have just mixed, if you have just Dirichlet and Neumann condition, so then suppose I choose this coordinate in this direction to be xa, and then this direction to be ya. Then you see that in the direction of ya, r has a negative eigenvalue. In the direction of x, r has positive eigenvalue. And there is no mixed component of x and y. And so that is required by this condition. So from that, you see that the y direction is Dirichlet. Dirichlet. And then x direction is Neumann. So from this matrix R should have these eigenvalues. And from that you can infer that this mixed component of the Kähler form should vanish. Okay? But we also know that as an n by n matrix, a 2n by 2n matrix, K mu nu is non-degenerate, because if you calculate the determinant of K mu nu, they should give you a volume form of the Calabi-Yau manifold. So it should be non-vanishing, non-degenerate. So we know this, but we also know that K mu nu is non-degenerate. So that means that KAB and KAB must be non-degenerate. So this in particular implies that A, B, which goes from 1 to P, and since A and B goes to 1 plus P, so this is unsymmetric tensor. And if you have an unsymmetric tensor which is non-degenerate, its dimension has to be even. So from that we can see that P is even. And we also know that given this, K as a matrix has to be block diagonal, where this is P, and this is equal to n minus P, or 2n minus P. And we have this block diagonal element. And these are 0. And so this helps you define complex structure on gamma. So this means that gamma is a holomorphic submanifold. And this condition means that actually omega restricted to that subspace. Yeah, sorry. So this means that this is a holomorphic submanifold. Okay. So we have learned that there is actually one type of D-branes, supersymmetric D-branes on Calabi-Yau manifold has to be of B type, and that implies that it has the holomorphic submanifold. So B type D-branes correspond to holomorphic submanifold gamma in Calabi-Yau manifold. Holomorphic submanifold means that locally you can describe this submanifold in terms of 0 of holomorphic functions. Okay, so we can also discuss A type. So if you have A-type Calabi-Yau manifold, A-type submanifold D-branes, on some cycle gamma, then this implies that K mu nu, R mu rho, R mu sigma is equal to minus K rho sigma. And then omega should satisfy this condition. Okay, so omega should satisfy these conditions. Excuse me, I think. Yeah, okay, so this is good. Yeah. So omega should satisfy these conditions. So this implies a totally opposite thing. So this would mean that the KAB is equal to 0 and KAB is equal to 0. But since K is a non-degenerate matrix, so in order for that to be non-degenerate, you have to have off-diagonal element. So that means that the K as a matrix has to have this structure. So now the diagonal blocks are 0. And you have non-trivial component over here where this is P and where this is 2n minus P. But you can easily convince yourself that if you have an antisymmetric matrix of this form, if K is antisymmetric, and if the determinant of K is non-zero, then it's a simple linear algebra question to show that this is only possible when these are square matrices. So then this implies that the P is actually equal to n, which is a half of the dimension. And on the half of the dimension, the k factorizes in this way. Okay, so such gamma, so for example, in the case of Calabi-Yau threefold, this such gamma is inevitably three-dimensional, real three-dimensional. So now it's odd dimensional. Such gamma is called Lagrangian. Okay, and so this terminology is taken from classical mechanics. So so you know that when you learn the advanced classical mechanics, you learn how to describe the equation motion using Lagrangian formalism and Hamiltonian formalism. And in the Hamiltonian formalism, you can abstractly describe it in terms of using symplectic form. So in the most general way of thinking about classical mechanics, you consider some even dimensional space, and you consider some symplectic form, which is an unsymmetric form. And so in the Hamiltonian formalism, you consider some kind of symplectic form omega, which is defined to be dpi with dxi summed over all the degrees of freedom. So this is an unsymmetric two form that is non-degenerate. And you can use this unsymmetric form to describe the Hamiltonian dynamics in the classical mechanical system. Okay, and this is asymmetric form, so you can think of Calabi-Yau manifold as an example of this phase space. Because Calabi-Yau manifold does have unsymmetric two form, which is non-degenerate. So you can formally think of Calabi-Yau manifold as a phase space of some dynamical system. And if you think of that in that way, then you ask, what is this subspace, which is half of the dimension for which the symplectic form actually vanishes, but in the direction along the subspace and in the direction transverse to the subspace, symplectic form is non-zero. This is just as if this subspace is a space of X, and the direction normal to it is the subspace of momentum. So therefore, from this perspective, if you view Calabi-Yau manifold as a phase space of some dynamical system, then the gamma is a half-dimensional subspace, which is like space of coordinate of the dynamical system, whereas the direction transverse to it is a momentum space. No, direction normal to it is a momentum space. Okay, so that's the sort of origin of this term, Lagrangian. So in general, in the symplectic geometry, when you have a submanifold, which is half dimension of the total space, on which the symplectic form vanishes, and in the normal direction, symplectic form also vanishes, then we call such a subspace as Lagrangian. So what we see is that if you have A-type D-branes, then in fact you can identify it as a Lagrangian subspace. And this condition basically means that omega gives you a volume form of this Lagrangian subspace. So this type of gamma is called special Lagrangian. This is a special type of Lagrangian submanifold for which omega gives you the volume form of this subspace. So what we see is that if you have if you construct a D-brane on Calabi-Yau manifold, and if you require that putting D-brane on that Calabi-Yau manifold preserves half of space-time supersymmetry, then essentially there are two types of such D-branes. One is characterized by holomorphic submanifold, and another is characterized by special Lagrangian submanifold. Okay? So these are useful classification, and you can actually do lots of precise, exact calculation involving these D-branes. And there are lots of things I could tell you about, such as the use of this notion. So there are a few very interesting applications of D-branes in Calabi-Yau. So one is, of course, calculating some non-perturbative effect in Calabi-Yau, but there are also several applications to mathematical physics. So for example, you can use D-branes in Calabi-Yau to, as I said, to study non-perturbative effect. And for example, to study, for example, the low energy effective theory in 4 dimensions, whether you can actually have, so how do you, so for example, in general, in low energy effective theory, there are lots of light scalar fields. And you'd like to see whether you can create a potential to make them massive so that it won't cause problem in phenomenology. And then you need to understand some non-perturbative dynamics to generate such a potential. And the D-branes have been used plays a very important role. There are actually applications to mathematics such as knot theory. So it is, as you may know, that the classification of knot and links in 3-dimensional space is a very interesting mathematical program. And there are, in the late 20th century, there was some big progress taking place because of the discovery of the Jones polynomial and the interpretation of the Jones polynomial in terms of the Chern-Simon case theory by Witten. You can actually translate that calculation in the language of string theory by using D-branes in Calabi-Yau space. There is an application of understanding of mirror symmetry. So mirror symmetry is a very interesting concept, relating seemingly different Calabi-Yau manifolds to be an equivalent in the context of string theory. And this has been very useful in calculating various quantities associated to Calabi-Yau manifold. And but D-brane can potentially help you understand how this mirror symmetry takes place in a microscopic way. So there's a very important work by Strominger, Yau, and Zastrow called the SYZ conjecture. And this is the following idea, that suppose you have a Calabi-Yau manifold, and suppose you have A-type brane. Gamma on this Calabi-Yau manifold. And suppose that there's a mirror pair of the Calabi-Yau manifold, which relates this Calabi-Yau to another Calabi-Yau with some kind of duality. Then you can actually show, and it is shown actually in my paper with Yaron Oz and Jen In, that the A-type D-brane on the original Calabi-Yau gets mapped to B-type D-brane in the mirror. And SYZ conjecture gives you sort of precise way of how this turns into each other. So there is actually potential relevance of the understanding how this takes place can actually give us insight into mirror symmetry, etc. So there are lots of many other applications of this. So there are things I could tell you more, but I only have a few more class left. So I think I should move on. So any questions about what I just told you? So this is about halfway today's lecture. So let me move on to another topic, which is probably the last topics I'm going to cover in this course, which is ADS-CFT correspondence. So let me first give you some general idea about the correspondence, and then I will show you some precise formulation. And so let's see. So this is an example of the holography of quantum gravity. So in quantum gravity, in the early 1990s, the first 't Hooft and then Susskind formulated a conjecture that motivated by the Bekenstein-Hawking entropy of black hole, that the information is stored in quantum gravity in a way that is very different from what you'd expect in the study of quantum field theory. So in the quantum field theory without gravity, the fundamental degrees of freedom are local. That you think that there is a local field, the Dirac field for fermions and scalar field and Maxwell field, and then at least in the perturbative level, you associate degrees of freedom at each space-time point, and then impose a canonical quantization condition. So that means that the degrees of freedom would increase like a volume. So therefore, for example, if you consider some region in space-time, and so you suppose you choose some Cauchy slice, and then you choose some space-like volume subspace in it, then the degrees of freedom with appropriate ultraviolet cutoff would grow like volume of the space. So, but the Bekenstein-Hawking formula for black hole entropy poses some puzzle because of the following. So this was the black hole entropy formula was originally conjectured by Jakob Bekenstein based on some thermodynamic consideration. But then Stephen Hawking discovered that in the semi-classical quantization of black hole, the black hole radiate thermal radiation. And by calculating the temperature of the radiation, he inferred the entropy of the black hole. And the surprise was that it actually agreed with Bekenstein's speculation, which meant that the entropy of the black hole grows like area of the horizon rather than the volume of the black hole. So one could have naively expected that if your black hole occupies certain region of space-time, then the degrees of freedom of the black hole should grow like volume of the space. But it turns out that the entropy of the black hole grows like area of the horizon. So this type of behavior motivated 't Hooft and Susskind to conjecture that if you have consistent quantum theory gravity, and if you apply that to some region of the Cauchy slice with a well-defined boundary, then the degrees of freedom inside of this gravitational system is not proportional to volume, but is proportional to the boundary area, and therefore the degree of freedom should be residing on the boundary. And therefore, they conjecture that there must be a formulation of quantum gravity in that region by using degrees of freedom residing on the boundary. Okay, so that was a speculation, and this is called the holography of quantum gravity. ADHCFT correspondence gives a precise realization of this speculation.
Oh, I have a question. Like the degrees of freedom you mentioned here is like pure like gravity or degrees of freedom or like gravity plus matter field?
I will explain this in this context. So I don't know how to answer this question in this general setup because this is a speculation, which is why ADHCFT correspondence is useful, because I can answer your question in the specific setup. So this is one of the use of string theory. So you can speculate a lot about quantum gravity, but string theory gives you a well-defined top-down construction, which tells you how such speculation should be formulated. So the idea comes from the following insight that type 2 A or B string theory has Ramon gauge field, and then there are charged objects. with respect to them. And these are black D-branes. And we have seen that there are two constructions of P spatial dimensional object extended in time that carries these charges. So P is even for type 2A, and P is odd for type 2B. And but there are two types of object. One is in terms of supergravity solution. And the other is in terms of D-branes. And but since this describes the same object with the same charges, so one might it's reasonable to expect that these are two alternative descriptions of the same object. So comparing how these are described in terms of these two approaches, we can find the correspondence. So that's sort of the idea. But let me be a little bit more specific. So in order to do the comparison usefully, we take some limit where both descriptions give rise to some useful information. So the limit we consider is a low energy limit. The limit where in space-time the excitation of degrees of freedom, the energy of the excitation of degrees of freedom in the theory is much lower than the scale set by string theory. Okay, so you might think that, well, so if you are considering energy scale that is much lower than the string scale, then there is no use of discussing it in the context of string theory. But you will see that there is actually some important role played by string theory too. Okay, so here's an idea. So suppose you have some black D-brane. In space-time, and it carries some Raman charges. So from the D-brane description, in this neighborhood, you can open string can end on it. And in the supergravity description, away from this D-brane, the geometry is curved. But if you are very far away from D-branes, you have asymptotically flat space. So you have a flat 10-dimensional space, and you have a supergravity theory. And then near this D-branes, you can in general have degrees of freedom localized on D-branes. So you can write this as a brane, S-brane. And then type 2, so the D-brane description tells you that these are given in terms of gauge theory. And then in general, there are interactions between them. So that is described by some additional interaction term in the Lagrangian. So in general, very far away from D-brane, you have supergravity theories. and you have interaction with brane degrees of freedom. And this description becomes better and better when the energy of the degrees of freedom we are studying becomes smaller and smaller. So let's in particular take the following limit where the energy measured at infinity is much smaller than the scale set by string theory. Okay? So remember, alpha prime is essentially L string squared. And so you're taking small limit of small alpha prime. So if you take this limit, then the Newton constant also becomes small. So for example, 10-dimensional Newton constant, 10-dimensional Planck scale, you can say is equal to G string to the quarter times L string. So that means that this is also much smaller than the 1 over Planck scale if string coupling constant is small. So we are considering the situation where the energy measured at infinity is much smaller than string scale and much smaller than the Planck scale. So in that case, the supergravity is almost free. First of all, the supergravity approximation becomes better because Planck scale, the energy that we are considering is much smaller than the Planck scale. But in addition, the supergravity theory is almost free because self-interaction between gravitons can also be negligible. So we also have almost free theory at infinity. And interaction between the degrees of freedom on the brane and degrees of freedom at infinity can also become negligible because these are gravitational interactions. So this becomes negligible. And then in low energy, the degrees of freedom on the brane is described by gauge theory. And in general, the Lagrangian for gauge theory starts from trace of F mu nu, 1 over Yang-Mills coupling constant square. But then there can be also higher derivative terms, like so for example, trace to the F to the 4th. But these are multiplied by alpha prime. So if each F is a border of the energy square measured at infinity. So therefore, this is also small compared to the first term. So in this limit, essentially, what you get in this limit, in this kind of description, what you get is the gauge theory, which is obtained as low energy effective theory of D-branes, isolated and without coupling to some purely free degrees of freedom at infinity. So essentially, modulo these uninteresting degrees of freedom, you have the low energy, you have gauge theory with the standard Yang-Mills Lagrangian plus finite number of degrees of freedom, finite number of matter, which can be derived from the D-brane description. So for example, if you have D3 brane, you have n equal 4 super Yang-Mills on D-brane. So that means that you have Yang-Mills gauge field with Yang-Mills Lagrangian coupled to 6 scalar fields and 4 fermions. So these are degrees of freedom you obtain in this description. So from this, you can see that in one description, if you take the limit, if the energy measured at infinity is much less than 1 over string scale, which is much less than 1 over Planck scale, then the R1,9 with black D-brane is described in terms of the standard Young-Mills plus finite plus matter field on D-brane plus decoupled free supergravity. Which we can ignore. So modulo this decoupled free degrees of freedom, you get D-brane. So for example, in this case, if you have D3 brane, then you get M equal 4 super Young-Mills. And if you have N D-brane, you have UN gauge unit. Okay? So this is one description. But there is an alternative view that one can offer in the same setup. So for that, I would like to remind you of the geometry. So to be specific, let's consider the situation of the D3 brane. So let's consider D3 brane. And suppose this D3 brane has N charges. So from the D-brane description, this is obtained by just considering same D3 brane on the top of each other. And suppose you have N D3 brane, then it has N charges. And that gives rise to, in the gauge theory description, UN gauge theory. But if you look for supergravity solution, then you have this metric. This is a volume form of the unit S5. Okay, and this is a radial coordinate. So this describes the radial direction from the D-brane. So you have this D-brane extended in some direction, and then there is R, and then there is a sphere. Okay, and this direction is 3 plus 1 dimension. Okay, and then F. So then this phi form, you have a non-zero phi form, and this F is given by 1 plus R to the 4 divided by R to the 4, where R is a constant defined to be the fourth root, or maybe R to the 4 is defined to be 4 pi G string times alpha prime times the number of D-branes or the charge. Okay? So this is a supergravity solution. But one thing I would like to note is that the time component of the metric is not constant. So GTT is equal to minus of 1 over square root of 2. So this has an interesting behavior because it goes to minus 1 for R goes to infinity. But F goes to 1 over R to the 4th near R equals 0. That is where the D-brane is located. So when R goes to small, F diverges. But this is minus square root, so this goes like R square divided by capital R square, where R goes to small. So TT component becomes small. So this poses this gives rise to the following interesting phenomena. So suppose you have you reside near the D-brane. You probe physics near the D-brane. And suppose this EP, P refers to this D-brane, is energy measured at distance r from the not distance but the position r away from this D-brane. Then on the other hand, if E at the infinity is energy measured at infinity, then E infinity is equal to f to the minus 1/4 of EP, where f is measured at distance r. So this is equal to r squared, capital R squared, divided by EP. So this is an interesting phenomenon. So this means the following. So we are interested in taking the low energy limit, I said, and but when I define the low energy limit as an excitation of state, degrees of freedom in this setup, where energy measured at the infinity is much lower than the string scale. So the energy measured at the infinity becomes small. But from here, what we see is that even if you have some excitation locally near the D-brane, whose energy is arbitrarily large, if that object, we are measuring that object near r equals 0, as seen at the infinity, it can be arbitrarily small energy. So what it means that if you have an object, if you take some object, some local excitation like you are some local excitation of the universe with finite energy. So therefore, your energy is non-zero. You have less mass, for example, and maybe you can have additional energy to it. But if I bring you to the near the D-brane, and if I measure it at the infinity, your energy can be arbitrarily small. And see by observer. So this is called the redshift effect. So this is essentially because of the time delay. So as you know that if you measure object near the black hole horizon, that the time seems to be flowing very slower near the black hole because of the gravitational redshift. So if the time flows very slowly, then as seen from infinity, the energy of that object looks low. So this is the same physics. So this is actually measured on this Earth. There is a famous experiment at Harvard, Pond and Prefker, I think. So they measured how the clock changes, the motion of the clock changes when you have gravitation. I think they measure that in one of the physics department building at Harvard, for example. You can also measure that by seeing some atomic clock on the Earth and on the airplane, etc. And so you have this is the same effect. This is a gravitational redshift effect. Okay. So that means that that we can have so that means that finite energy excitation at D-brane can be seen as having zero energy at infinity. So this has two effects. The one effect is that in this limit, therefore, you can isolate the degrees of freedom, but inside of in the neighborhood of D-brane, you can have arbitrary excitations. And another is that since as seen from infinity, it has negligible energy. So even if in the neighborhood of D-brane you can have arbitrary energy excitations, but these excitations cannot climb the gravitational potential to escape to infinity. So that also has a decoupling effect. So this is related to this decoupling effect of the bulk and the boundary degrees of freedom. But from this supergravity description, this arbitrary energy excitation near the degrees of freedom can be isolated by just focusing on the region near r equals 0. And in that region, you can have any excitation, including stringy excitation or D-branes or whatever you like. So you can ask then what kind of excitation? So we can have any excitation of type 2B string set near r goes to 0. So this is type 2B because here we are considering this D-brane. Have almost 0 energy. At infinity. So those should be included, therefore. So here I have this description. Here I have told you that from D-brane description, if you take the limit when you see the physics, you only focus on the physics of energy excitation, physics of excitations whose energy is much lower than, is negligible at infinity, you extract the D-brane description. So here, in the same limit, we can extract any excitation of type 2B string theory near r equals 0. But in the limit of r goes to 0, f can be replaced by, we can neglect this one, so we can replace f by 1 over r to the 4th. So we can write f to be almost equal to r to the 4th divided by r to the 4th. And the metric becomes r squared minus dt squared plus dx1 squared plus dx2 squared plus dx3 squared plus r squared dr squared over r squared plus r squared d omega 5 squared. But this geometry is nothing but that of the 5-dimensional unfiltered space times 5-dimensional sphere. So this argument shows that if you have, so these two descriptions are the same. On one hand, here you have just, in this case, 3 plus 1 dimensional n equal 4 super Yang-Mills theory. But in this description, we can consider any excitation of type 2B string, full type 2B string theory in ADS5 cross S5. So this is very interesting correspondence. On this side, the full string theory is restored, or is not about full. We can keep full string theory, including any stringy excitations or D-branes or whatever you like in type 2B string theory in this geometry, because any excitation like that has almost 0 energy at infinity. But in the same limit, in this description, you have just low energy excitation of open string on D-brane. So you just have the standard Yang-Mills Lagrangian with finite number of matter field, and that's all. So this is a correspondence. And so this argument was originally presented by Fuamara-Sen as a historical paper in 1997, and then this has been refined and tested in a variety of circumstances, and we have full confidence about this correspondence. So for the next couple of lectures, I would like to explore a variety of aspects of this correspondence, try to formulate it more precisely, and then discuss a variety of consequences.